Oh, um, I just want to some disturb the line. Okay. Okay. Okay, for this week, okay, we will discuss on the classical analysis based on engineering plasticity. Okay. So I will give some brief introduction. Okay. Then we may have basic understanding of sonics. So then I will discuss on the how the plasticity works. Okay. On the on the applications of horizontal that we use when we want to design for the so this is week number 1. Okay. So this model aim to develop a conceptual understanding and analytical ability of students to develop solution to a range of advanced geotechnical problems. Okay. So this model cover the following topics. Okay. Geotechnical analysis based on engineering plasticity. Okay. So we discuss the upper bound and lower bound theorems. Okay. Stress discontinuities. Okay. So when we deal with a different orientation of failure plane, okay, we will rely on the stress discontinuities approach. Okay. So collapse load for drains and undrained conditions. Okay. So let's say if we deal with sandy material or a clayey material, so then we use the approach of the soil plasticity, okay, to determine the capability of the soil to sustain the loads, okay, or to identify what is the collapse loads. Okay. So application of engineering plasticity to various field problem, okay, so such as earth pressure coefficients for rough retaining wall, wall with non-horizontal backfill, and foundation with inclined loads. Okay. So for the first discussion, okay, we will go for the very basic approach on the retaining wall. Okay. For the next 4 weeks, okay, we will discuss on the to the non-horizontal organism. Okay, so then this application also can be used, okay, for the foundations, either by either has been applied on a vertical or an inclined loads. Okay. So as I mentioned before, I will also cover on the calculation based on retaining wall and shallow foundation by referring to the conventional, okay, which is the British standard, and also with the use of the Eurocode 1997, which is Eurocode 7, okay, on how to determine the stability of the geotechnical structure, especially on the retaining wall and shallow foundations. So upon successful completion of the topic, student will be able to analyze routine and non-routine geotechnical problems under both drain and undrained loading conditions using the classical analysis method based on engineering plasticity. Okay, so that will be the main target, okay, from this lecture. Okay, whereby at the end of this, at the end of the of this topic, okay, so we able to quite suddenly, okay. So you are be able to understand on the how to design, okay, or to analyze. Can you still see my slide?
No,
Yes, sir.
No, no, yes.
Yes.
I think internet, I think. It's
Oh, you
loading.
cannot see. Still loading.
No, I cannot see the.
Oh,
I can see the slide now.
It's loading for me.
still loading.
Yes, loading. Ada dah.
Ada. Sorry, because I'm not using, yeah, because usually when we are in our university, so we have a better internet connection. Oh, it's loading for you. Okay. So wait for a while. Because I'm using the home internet. Okay, okay. But the voice is okay, the voice.
Voice is okay, sir.
Yes.
Yeah. Okay. Okay, using classical analysis. So plasticity is called a classical analysis. Okay, because it's a is the pioneer, okay, for the other analysis method later on. Okay. Okay, so we go for the essential soil mechanics concept. Okay. Okay, so just imagine, okay, we have a solid body of a soil. Okay. Okay. So this is a body of soil. Okay. So in three-dimensional. Okay. But later on, it's more easy, okay, to consider as a plane strain or a 2D, okay, rather than this three-dimensional view. Okay. So the load and force applied to a solid body, such as a mass, are distributed within the body as a stresses. Okay. So we have x-axis, y-axis, and also z-axis. Okay, so the normal stress will be acting 90 degree. Okay, to the what we call to the uh, to this area. Okay, and also for the shear stress will be acting parallel to uh, the this area. Okay. So same goes to the what we call as to the this plane, okay, where the normal force will be acting perpendicular and the shear force will be acting, the shear stress will be acting at the parallel to this plane, okay, and also on this plane as well. Okay. So provided there are no plane of weakness that might interrupt the transfer of stress, it is usually assumed that the stresses vary smoothly and continuously throughout the body, which is then as a continuum. Okay, so means that based on this small solid body, so we just imagine for the whole mass of the soil, okay, so it will behave at the same stress conditions. Okay, they call as a continuum. Okay, so first we look on the shear stress. Okay, they call as a tau. Okay, so we have x and y. Okay, what does it mean with x and y? Okay, for example, where is tau x? and y. Okay, so this is tau x and y. So the first subscript, in this case, x, denotes that the direction of the normal to the plane on which the stress acts. Okay, while the second subscript, in this case y, denote the direction in which the stress acts. Okay. So if we deal with the normal, means that it is related to the perpendicular direction. Okay. When we deal with what we call as the same plane, so it is related to the parallel. Okay. So for this case, the tau is acting normally on the axis of x and perpendicular to the axis of y. Okay. So usually for the normal stress, okay, it will acting on the same axis. However, for the for the shear stress, okay, it will acting on the normal plane, okay, on which is perpendicular to the direction of the axis and parallel to the another side of the axis. Okay. So in soil mechanics, it is easier to take compressive direct shears and strain and anti-clockwise as viewed from inside the element, shear stress and associated shear strain as positive. So we need to standardize the approach. Okay, as mentioned here, if there is a moment, okay, or the movement, okay, so we consider the anti-clockwise as a positive. Okay, while if there is a clockwise movement, so later on we will use the negative. Okay, so compressive, it is related to how we compress soil. Okay, it's a compress and there will be another action of tensions. Okay, so if tensions, it is related to clockwise and we may consider as a negative. Okay? So it depends. If you feel that you are comfortable to use anti-clockwise as a negative, then clockwise as positive. So you need to standardize it. Okay, anything related to anti-clockwise, if you choose to use negative, and clockwise later on you need to use as a negative, positive, for example. Okay. Okay. So geotechnical engineer are people who like to simplify matters. Okay. So that's why later on we will not concentrate on the three-dimensional condition. Okay. So then we try to simplify it to make it more easy to understand. Okay. But in reality, we deal with three-dimensional conditions. Okay. So we don't like to deal with stress condition, having both normal and shear stress all the time, as in the previous figure. So we normally assume that the face of any soil cube element are principal plane. Okay. So later on, the shear will be included inside the principal plane. Okay. So there is no shear stress acting on them. So the stresses on the soil cube element shows in the previous figure now look like the next figure, or look like this this type this figure. Okay. So no shear plane shear stress on all planes. Okay. So let's say if the stress, normal stress is sigma z, it is greater than sigma yy and sigma x, then the sigma z, sigma yy, sigma S are known as the major, intermediate, and minor principal stress respectively. Okay. So then, okay, to make it more easy, okay, usually we use sigma 1, sigma 2, and sigma 3, okay, in the place of sigma ZZ, sigma YY, and sigma XX respectively. Okay. Later on, we may use this approach when we want to derive for the lateral stress of a soil, okay, that we will use to analyze for the retaining structure. Okay, okay. So this is in three-dimensional. Okay, so a condition known as a plane strain condition by neglecting the stress or displacement and stress of the retaining wall in the lengthwise directions. Okay, so we just imagine that we have what we call as a retaining wall with a certain length direction. Okay, so in order to ease our calculations, okay, so we may assume it is in a plane strain conditions. Okay, so we may neglect the strain or displacement and stress in based on the length directions. Okay, that's why when we design for a retaining wall, okay, although the value is in loads, okay, we may assume it is in kilonewton per meter run. Okay, so means that for every 1 meter, that is the load applied on that 1 meter length. Okay, so this is because the length of retaining wall is far larger than its width, and the movement is predominantly along its width. So that's why we measured it for every per meter run. So simplified thing by assuming strain in the lengthwise direction is 0, therefore stresses can be ignored. Okay, so then they introduce, okay, what we call as a plane strain condition. Okay, so yeah, but currently, okay, there are lots of software or numerical tools, okay, that's been used to analyze based on a three-dimensional view. Okay, so in that case, okay, it is better to use what we call as these 3D numerical tools. Okay, for example, if we deal with scattered arrangements of file, okay, so it's very difficult to put it in two-dimensional. Okay, so it's better to use the three-dimensional, so then we can put or arrange the file according to the condition of the site. Okay, but for a very basic, for a very good analysis, okay, so then the use of the plane strain condition is good enough. Okay, so from there, okay, since we can simplify the stress condition in any element of the soil within the retaining wall or soil body, so then the principal plane and principal strain approach is possible to be used. Okay, so the stresses acting on cross-sectional plane of the soil look like below. Okay, so then we have the sigma 3, sigma 1. So inside the soil or inside the what we call it inside the square shapes, okay, or the soil body, okay, so there will be stresses or the shear stress and also normal stress acting inside it, okay. So this means we need only to consider the sigma 1, okay, which is 1, and so the sigma 3 in order to understand the behavior of the inside the soil body. Okay. Okay, by simplifying the condition into principal plane and plane strain does not mean the shear stress do not exist at all in the soil. Okay, so within the soil element, if you rotate by a mass s, there will be a shear stresses, okay, occur. Okay, so this makes sense if you consider it's more circle. Okay, so to include what we call as the shear stress, okay, in our analysis, okay, so then we need to use the approach, okay, by plotting the more circle. Okay. Okay, so this is a typical more circle column, a more column circle. Okay, okay. Based on the more column circle, okay, the rotations of the theta within the soil element is equivalent to the 2 theta in the more circle. Okay, later on I will relate this 2 theta and the theta, okay, when we want to get the coefficients of active lateral pressure and the coefficient of passive lateral pressure. Okay? So how they obtain the equations, okay, by understanding on the more column where 2 theta actually represent the rotation of theta within the soil elements. Okay, so the directions in this case anti-clockwise in the soil element remain the same when you in the more circle. Okay, so as we have mentioned before, okay, for the comprehensive, when we compress the soil, okay, in the more column circle, okay, we consider as the anti-clockwise directions. Okay. So beside the stress along the sigma prime, in this case, is an effective stress axis, you will always have a shear stress on the circumference of the circle. Okay, so we include the what we call as the as the x axis, the y axis, and the effective stress on the x axis. Okay, why we choose to use the effective stress? Okay, to relate with the tau. Okay, so because the effective stress only consider the stress that happen inside the soil body. Okay, so if the total stress means that a combinations of the effective stress plus the pore water pressure, whereby the pore water pressure or the water cannot experience any shear stress. Okay, the soil only experience a shear stress when we start to compress the soil. Okay, okay. Later we may derive an equations, okay, for the drain and undrained conditions, okay, to analyze for the lateral force, okay, that acting, okay, on any retaining wall, okay, inactive passive. So we may the how do I look? Okay, as I mentioned, as I given to you, okay, the last notes, okay, on the derivations, okay, you can understand. You are not using the equation only, but you know how the derivation works, okay. So it require a lot on the understanding on the trigonometry, okay. So I need to learn again the trigonometry, okay. So then there are sub explanation on the trigonometry. They call as a trigonometry identity. Okay. So actually we learn it, okay, during our secondary school and also during the mathematical engineering subject. Okay. Okay. Okay, so that is for the more column plane strain, okay, concept. Okay, so now we may relate with the drain and undrained conditions. Okay, so then we use the sigma prime for effective stress analysis if the geotechnical event involve coarse drain soil or for long term stability analysis in fine grained soil called effective stress analysis. Okay, drain shearing essentially means that the soil during the soil shearing, the water is drained out of the soil. Okay, so that is for the effective stress approach. Okay, so the effective stress approach usually defined as a long-term stability. Okay, while for the use where we use the sigma, okay, for total stress analysis, for analyzing the short-term stability of geotechnical event in fine-grained soil, okay, they call it a total stress analysis. So undrained shearing means that the water cannot drain out of the soil during the shearing. Okay, so usually when we deal with what we call as a design for a foundations or for a pile foundations, okay, we use the short-term stability, okay, because we want to get what is the capacity of the foundations right after we apply for the loads. Okay, so that is considered as a short-term stability. Okay, so usually we use the total stress concept. Okay, when we want to design or to look on stability, for example, for a slope, okay, we want to look on the performance of the slope for the longer times. Okay, so then usually we use the effective stress approach. Okay, so the effective stress approach means that we use the C and phi prime, okay, that usually we obtain from either from consolidated undrained or consolidated drain triaxial test. Okay, but in terms of the behavior, okay, usually in EC7 at the drain conditions, okay, based on the soil, where the soil is able to drain out the water inside the soil particles. Okay? Usually it represents for the what we call as sandy type of soil. Okay? While for the undrained, usually it related to the clayey type of soil, okay, where the soil or the water, okay, is unable to be drained out, okay, during the shearing conditions. Okay? So that is the approach used by the EC7 to describe the behavior for the sandy and clayey type of soil. Okay, so the total stress sigma is equal to the effective stress plus with the pore water pressure. Okay. So this is the total stress, okay, where it includes what we call as the stress acting on the soil fabric, and at the same time the stress from the pore water pressure. Okay, how to determine the total stress? Okay? So then you need to understand on the unit weight of the soil. Okay? Then you need to determine it based on the height or the thickness or the depth of the soil below the ground. Okay. So for example, okay, for example, so this is the depth. Okay, we retrieve the soil at 3 meter deep. Okay. So then, okay, so the soil unit weight is about 17. Okay. Then there is a groundwater level at 1 meter below the ground. Okay. So the saturated unit weight is just plus one more. So the unit is kilonewton per meter cube. Okay. So the unit weight for gamma saturated is 8 kilonewton per meter cube as well. Okay. So in order to calculate for the total stress, okay, so 17 times 1 plus 18 times 2. Okay, so that is the total stress value. Okay. So to get the effective vertical stress, okay, so this 17 times 1 plus 18, we need to exclude the unit weight of water because it may contribute to the pore water pressure. So usually unit weight of water, okay, either we use 9.81 or it is easy to use 10. Okay. So 18 minus 10, 8, then multiply with 2. So that is for the effective vertical stress. Okay. The last one is the pore water pressure. The pore water pressure only count when there is a groundwater level. Okay? For example, for this case, okay, the pore water pressure is 10 times 2. Okay? So that is the pore water pressure value. Okay, so that is how we determine the total effective stress and pore water pressure. Okay. All right. So that is a little bit drain undrain, effective and total stress analysis. Okay. So in terms of design, okay, analysis, okay, so we may refer to the limit theorem of plasticity. Okay. So as an engineer, we need to make sure that the structure to be built can be supported by soil. Okay. For example, okay, so okay, so let's say this is the schematic diagram. For a single story building, okay, with the use of shallow foundations. Okay. So for example, the load, okay, the load from the roof, okay, will be transferred to the roof beam. Okay. So then the load from the beam will be transferred to the, what we call as to the column. Okay. Then the load from the column, okay, later on will be distributed, okay, to the beam, ground beam, okay, and with additional loads from the slab also will be transmitted to the ground beam. Okay, so that for each column, okay, there will be a load from the column, from the beam, and from the slab. Okay, so this combination of load, okay, will be transmitted to the substructure, okay, which is in this case is a shallow foundations. Okay. So from the shallow foundations, it will transfer the load to the soil. Okay. So that is the concept of load transfer mechanism for a building to the to the substructure and to the soil. Okay. So we need to know how much load or pressure can the soil support it. Okay. So we name it ultimate load or pressure. So that is the maximum load can be catered by the soil. Okay. The philosophy of the designing any structure at the ultimate pressure is known as the ultimate limit state design. Okay. So we call it as ultimate limit state design, ULS. Okay. While the serviceability limit state, SLS design involves excessive deformation leading to damage or loss of functions. Okay. So we need to understand there is a ultimate limit state. Okay. Means that the stress is the maximum value that can be sustained by the soil. Okay? If it exceeds the ultimate limit state, so means that there is a possibility for the any geotechnical structure collapse. Okay. So when we has identified the ultimate limit state, okay, for example, for a simple shallow foundation, okay, so we use the Meyerhoff or Terzaghi equation, okay, to calculate for the what we call as for the ultimate stress, okay, which is the QULT, okay. Then we divide it with the factor of safety. Okay, we divide with factor of safety. Okay. Once we have divided factor of safety, so that is count as a design load or design stress. Okay. So this design stress will be related to the deformation or settlement. Okay. If we apply it for a certain period of service or time. Okay. So this design load is related to the serviceability limit states. Okay. So it can involve an excessive deformations. Okay. If the design stress or design load, okay, has made the soil to deform in a very high or excessive magnitudes. Okay? So if the soil experience an excessive deformations, so it can lead to a damage or loss of function. Okay, so it means that the serviceability limit states is related to the function of the building. Okay, and to measure the function of the building, okay, so we need to identify if there is a settlement occur, or it can be shown, okay, based on the crack, okay, that occur on the building itself. Okay. So and also it related to comfortness of the people who stay inside the building. Okay, people will not feel comfortable, okay, when we stay in a house that has a lot of crack. Okay, although the building is considered stable, okay, and safe to be staying. Okay. But it loss of the function, people not feel comfortable. Okay, so then the severity limit state is more related to the soil deformation or soil settlement. Okay. However, for the plasticity theory, it is limited to the ULS design only. Okay. So for this SLS, it is more related to the elastic theory. Okay. So when we discuss on the plasticity, okay, we will not discuss on the soil deformations. Okay. Only on the ULS issue when we deal with soil plasticity. Okay. So the geotechnical engineers are using the concept of plasticity to estimate the ultimate pressure or the collapse load. Okay, the collapse loads includes the applied load system and body force. Okay, the collapse loads can be determined using the limits theorems of plasticity, also known as limit analysis, to calculate lower and upper bounds to the true collapse loads. Okay, so we have the collapse loads, okay, or limit state. Okay, in order to estimate or to determine, okay, what is the collapse loads, so then we need to use what we call as the upper bound and lower bound approach. They call as a limit analysis. Okay. Okay. So for the plasticity concept to work, the soil is assumed to obey the rigid plastic stress strain behavior, okay, where both yielding and irrecoverable shear failure occur at the same state of the stress unrestricted plastic soil flow take place at this stress level. Okay, so the rigid plastic concept is shown in the figure below. Okay, so yeah, there is a lot of soil constitutive model. Okay, this is the simple approach. Okay, where we can easily estimate, okay, by using a mathematical calculations. Okay, let's say if we want to do some predictions for the shallow foundation, so we need to assume, okay, that its behavior is in rigid plastic behavior. Okay? Although the limitations, it is not similar to the what we call as the stress strain behavior of the actual soil. Okay? Because the actual soil, there should be an elastic deformation and then continue with the plastic deformation. But yes, we assume that the yielding and irrecoverable shear failure occur at the same states. Okay, so means stress and unrestricted plastic soil flow, okay, have the same stress level. Okay, for example, saya mak dia hang. Okay. For example, for a normal stress strain, it has this elastic condition, then it reach the yield of plastic peak. So for this rigid plastic stress behavior, okay, we assume it has a straight line. Okay, so this is a very simple approach, okay, that we can use, we call as a mathematical calculation later on, okay, by using this rigid plastic stress strain behavior. Okay. Okay. This is the typical stress strain behavior of a soil. Okay. So then to estimate what will be the ultimate load for this stress strain the behavior of the soil. Okay, so then we need to estimate by using the upper bound and lower bound approach. Okay, so the applied load system, including body force for this condition, is referred as the collapse loads. Okay, we can determine the collapse load using the limit theorems of plasticity, also known as the linear basis, to calculate lower and upper bound to the true collapse loads. Okay, so means that we have the upper bound and the lower bound. It looks like an envelope. Okay, we have upper and lower. Okay, so to get the true, what we call as the ultimate soil failure. Okay, so we need to make sure that the lower and the upper bound converge. Okay? So it means that the result will be the exact value of the collapse loads. Okay? So to make it converge, so we need to use a very small elements, okay, during our calculations. Okay, I will show later when we discuss on the upper bound and lower bound. Okay, so we need to use a very small match, okay, in our calculation, okay, to get the lower and upper bound converge each other. So the limits analysis is based on two theorems of facility, which are lower bound theorems and also the upper bound theorems. Okay, what does it mean with lower bound theorems? The lower bound theorem states that if a stress at any point in a soil does not exceed the failure criterion for the soil and is in equilibrium with the external load inclusive self-weight of the soil, the external load represents lower bound to the true collapse loads. Okay. In short, if it can be shown that the soil can carry the load, then it will. Okay, because based on the lower bound still the lowest still lower than the failure collapse load. Okay, so this is the actual failure loads, okay, or actual capacity that can be retained by the soil. Okay? So the lower bound is lower compared to the ultimate value. So the same goes to the upper bound. So it means that it is above the ultimate load. Okay. So if a mechanism of plastic collapse is kinematically admissible, okay, so it is proof that it is kinematically admissible. Okay, the work done by the external load, inclusive the body force or self-weight of the soil, is equal to the energy dissipated within the soil mass as it deformed. Then the X represent the upper bound to the true collapse loads. Okay. In short, if it can be shown that the soil can fail, then it will. Okay. So that is the upper bound. Means that it is an approach to estimate, okay, a little bit higher compared to the actual ultimate loads. Okay, so in that case, we need to design lower than the upper bound value. Okay. Okay, in plasticity theory, okay, based on Hill and Calladine, okay, the characteristic of the yielding, hardening, and flow are considered. These are described by the yield function, a hardening law, and the flow rule, respectively. Okay, this is lecture only limited to the yield function and associate flow rules because the flow rules is related to the uh, elasticity. Okay, so the yield function related to the plasticity. Okay, the yield function is the return in terms of the stress component of principal stress and define the yield point as the function of a current effective stress and the stress history. Okay, the more column failure criterion is one example of the yield function if perfectly plastic behavior is assumed. Okay, so the more column is the simple approach to be used to identify the yield conditions. Okay, flow rule, the flow rule is specific the relative magnitude of the plastic strain components during yielding under a particular state of stress. Okay, so the flow rule is more related to the plastic strain components. Okay, okay, soil as a frictional material. Okay, so it is more related to the sandy type of material. Okay, so then we explain it as a drain approach. Okay, Column original proposed that the limiting strength of the soil was frictional or interparticle frictions. Okay, so you have heard about the phi. Okay, so phi is considered as the interparticle frictions. So friction is commonly described by T equal to the new N. Okay, so sorry. So this is T and this is the N. N is the normal stress, while T later on is count as a tau. Okay, where T is the limiting friction force and N is the normal force acting perpendicular to the slip plane and the nu is the coefficients of frictions. Okay, so as described in the figure 7a, we show the frictional strength along a plane of slip. P is the strength of an assembly of particle along a plane of slip. So in an plane of soil, we use the shear stress and normal stress, okay, which is tau, okay, is equal to tangent phi times what we call as the effective normal stress, okay, or effect sigma prime, okay, or the tangent phi is equal to the tau over effective stress. When where tangent phi is equal to the coefficient of frictions, which is an intrinsic material property related to roughness of the shear plane. Okay, so it is a intrinsic material properties. Okay, because it deal with the shape, size, and angularity of the soil particle. Okay, so the shear strength of the soil at the point on the particular plane is normally expressed as a function of effective normal stress, because the shear stress in the soil can only be resisted by the skeleton of solid particle and not the pore water of the soil. inside the soil. As I mentioned before, okay, when we consider for the shear strength, okay, we only deal with the soil fabric or skeleton of the solid particle. So that is why we use the effective normal stress when we plot the relationship between the tau and the sigma prime. Okay. Okay, so this is an example, okay, how more column model was inspired, okay. So it is based on simple analogy, okay, friction generated when a block moves along a rough surface, okay. So when we, sorry. Okay. Okay, then we have a normal force, okay, acting on a block, okay. Then we have a lateral force that push, we call as the block, okay, to be moved, okay. So then there will be a frictions, okay, occur, okay, which is count as the T, okay, or tau is the F over A, which is the area, okay, which is the directions is on parallel to the plane, and the N normal force is count as active, which is N over A. Okay, so where tau is the shear stress and effective stress is the normal vertical stress. Okay, so this gives tau is equal to effective stress tangent phi, okay, to get the shear stress value of the soil. Okay, then productions of the, okay, for a drain analysis. Okay, so we have drain and then we have an undrain. Okay, so for the drain analysis, okay, so this is the shape of the more column. Later on, I will show the shape of the undrained soil. Okay, so the stress state for a 2D element of soil can be represented by a Mohr circle defined by the effective principal stress, sigma 1. So this is sigma 1 and sigma 3. So the Mohr column failure envelope is derived from the frictional model. However, it's difficult to deal with the non-linear part of the envelope associated with the interlocking. Okay, so we only concentrate on the frictional conditions. Okay, rather than that, it's very difficult. Okay, so therefore, okay, for this is for the this value is for the undrained. Okay, while this value is for the drain. Okay, therefore, it is common practice to approximate the straight line of the failure envelope by tau f equal to c, which is this value at the tau plus effective vertical stress times with the tangent phi. Okay, where C and phi are the shear strength parameter referred to as cohesion intercept and the angle of shearing resistance respectively. So from this more column, later on, we can get what is the C and the phi value. Okay. While this is for the undrained, okay. So for the undrained, the tau max is equal to the tau u as u. Okay. The radius of the more column of total and effective stress are the same because water cannot take shear. Okay. Since the excess pore water pressure generated during undrained loading can be difficult to quantify, it is convenient to use an alternative failure criterion for the short-term failure of the soil clay based on total stress. Okay. So means that to assume or to determine what will be the strength, okay, so by neglecting the effect of the pore water pressure, so the tau max is equal to the radius of the more column for this undrained analysis. So on the plane of the maximum shear stress, tau max is equal to the SU is the undrained shear strength. Okay, for a soil of obeying the maximum shear stress, failure criterion tau max is equal to tau u or Cu or Su. The maximum possible difference between the vertical and horizontal total stress sigma h may be obtained by considering more circle of the total stress at failure. For a given vertical stress sigma v, as illustrated in the figure, the minimum horizontal stress cannot be less than, okay. So when we discuss on the vertical stress, okay, so the tau max is equal to the tau u, okay. But when we want to derive for the horizontal sigma h, okay, later on we may use this approach, okay, which is sigma h is equal to sigma v minus 2 su for the active, and sigma h is equal to sigma v plus 2 su for passive. Okay, later on, I will show to you how to derive this equation, okay, to get the relationship between the sigma h and sigma v for the undrained and also for the drain based on the horizontal stress analysis. Okay, so that is all for the some of the explanations on the soil mechanics, okay, that later on we can get an idea when we want to look on this limiting earth pressure from limit analysis. Okay, before we go for this limiting earth pressure from limit analysis, okay, so I have give you a PDF on example 1. Okay, so it describe little bit, okay, on how could we calculate for the total stress, effective stress, and also the pore water pressure, okay, and how to construct for the more column circle, and then determine the value, which is I described before, the C and the phi, and also to determine the tau value. Okay, so we move first for the example number 1, okay, which is I already give it to you before. Okay. Look on the example number 1. Okay. Okay. Can you see this? You see the PDF file, or it's still still in the PowerPoint? Let me stop this. Alright. Okay. Okay. So look on the example number 1. Okay. So I also give the solutions there. Okay. So what is the shear strength in terms of effective stress on a plane within a saturated soil mass at a point where the total normal stress is 295 and the pore water pressure is 120? Okay, so now we want to get what is the effective stress in order to get the shear strength. Okay, so the effective stress parameter of the soil for the appropriate stress range are C is equal to 12 and phi is equal to T. Okay. So first, we already given with the total normal stress, 295. Okay. Then also the pore water pressure. Okay. So to get the effective vertical stress, okay, so 295 minus 120, so the value is 175. Okay. So based on the more column equations, okay, the shear strength can be estimated by using the C plus effective stress tangent phi. Okay? So then the C is equal to 12, the phi is equal to 30. So then 175 tangent phi. So the shear strength is equal to 113. Okay? So that is on how to calculate for the what we call as for the effective or the normal the shear strength. Okay. Okay, for example, okay, I need to open in Google, sorry, in Microsoft Edge. Wait. Okay. Okay, basically, okay, okay, the idea is how could we determine the confining pressure when we want to conduct for the triaxial test, eh? Okay. Okay. First, we need to know how to read the soil investigation report. Okay. So usually we use the borehole or the bore log. Okay. So in the ball log, they identify what we call as the soil to be for the laboratory testing as the undisturbed. Okay, they call it a UD. Okay, so when we read the ball log, okay, we identify where is the depth that they collect for the undisturbed sample. Let's say the depth is 3 meter. Okay. Because based on the boring procedure and the SPT for every 1.5 meter deep, so then they need to conduct for the SPT. Okay, so 3 meter, okay, they gain the undisturbed sample. Okay, so then they send to the lab. Okay, so as an engineer, okay, we need to know what will be the confining pressure, okay, to be used in our triaxial testing. Okay. So because we need to have a series of confining pressure value. Okay. So and it should represent the actual confining pressure at the field. Okay. So for example, if we retrieve the soil at 3 meter deep, okay, so then the confining pressure that can we suggest is 3 times the unit weight of the soil. Okay. This is gamma. Okay. So usually the unit weight can be estimated based on the SPT, standard penetration test, or we can measure it, okay, at the lab. Okay. So then this unit weight multiply with the 3 meter, so that is the suggested confining pressure that we should apply. Okay. So 3 times 18, for example, then we receive 54. So this 54 is can be counted as a confining pressure, sigma 3. Okay, okay, sigma 3. So can be counted as a sigma 3. Okay. So that is the confining pressure that can be applied. Okay. So then we do the shearing test, okay, to determine what will be the shear strength value. Okay. From there, we obtain the C and the phi value. Okay. So then this C and phi, okay, we may include calculation of the tau to estimate the shear strength of the soil. Okay. So that is for the Q1. Okay. Okay. Now we go on the Q2. Okay. A series of grain triaxial tests were carried out on specimen of a sand prepared at the same porosity, and the following results were obtained at the failure. Okay. Determine the value of the angle of shearing resistance, which is the P. Okay. So all round pressure is what we call as the sigma 3. Okay. So the principal stress difference, okay, is the value of the sigma 3, sigma 1 minus the sigma 3. Okay, so this is the difference. Okay, then to get the sigma 1, okay, means that the all round pressure should be add with the principal stress difference. Okay, so then we make a table, okay, which is the sigma 3, okay, 100, 200, 400, and 800. Okay, so the principal stress difference is equal to sigma 1 minus sigma 3, okay, which is 4 to 5, 5 to 4 to 5, 4, 5 to 908, 1810, and 3624. Okay. So later on, to determine the sigma 1, okay, because the sigma 1 value and sigma 3 value will be used to construct for the more column circle. Okay. So let's see if the principal stress difference, the equation is sigma 1 minus sigma 3. Okay. So to get what we got as the sigma 1, so sigma 1 is equal to 452 plus 100. So then the value is equal to 552. Okay. So then 1108, 2210, 4424. Okay. So later on, we plot this, we represent the sigma 3, this is sigma 1. Okay. So sigma 3 is the confining pressure. Sigma 1 is the ultimate failure. Okay. So once we have plot, okay, so then we can get what is the failure envelope based on the sigma, based on the phi value, which is 44. So in order for you to plot this more column diagram, okay, you need to have what we call as a compass, okay, to draw the half circle of the more column diagram. Okay. So then okay, in a series of unconsolidated undrained triaxial tests on specimen or fully settled clay, the following result were obtained at failure. Determine the value of shear strength parameter CU and FU. Okay, so the same approach. Okay, we have all the round pressure and per stress difference 200, 400, 600. Okay, so that is the all round pressure. Okay, principal stress difference is 222, 218, 220. So that is now the failure value. So then to get the failure value, 222 plus 200, 218 plus 400, 220 plus 600 to get the sigma 1. Okay. So once we retrieve or draw the more column diagram, So we found that, okay, for this UU test, okay, is equal to the CU of 110 and phi U equal to 0. Okay, because usually for the UU test, if the soil is clay material and fully saturated, so we may gain this kind of shape. Okay. Okay, the first one is drain triaxis. Okay. So then this is the U and the last one the U. So the result below were obtained at failure in series of consolidated undrained triaxis tests before water pressure measurement on specimen of a fully saturated clay. Okay. So the value of the shear strength parameter C and P if a specimen of same soil were consolidated under an all pressure of 250 and the principal stress difference applied with an all-round pressure change to 350. Okay. What would be expected value of principal stress difference at failure? Okay. So then sigma 3 is equal to 150, 300, 450, and 600. Okay. So then we have sigma 1 minus sigma 3, okay, which is at the fail, which is the difference, 103, 202, 305, 410. Okay. So later on we will have a two line. Okay. We need to determine what is the effective value we have there for water pressure. Okay. Means that we can have two different approach. The first one, the total stress. The second one is the effective stress. Okay. That's why I mentioned that we can have two different more column line. Okay. But for this case, we need to get the C prime and P prime. Okay. So to get the C and an effective stress approach or stress value. Okay, to get the effective stress value, so we need to get or include the pore water pressure, okay, in the calculation, okay, to determine the effective stress value. Okay. So for example, the pore water pressure here is 82. So 150 plus 103 is equal to 253. Okay. Then to determine the effective stress of sigma 3, okay, so 150 should minus with the 82. Okay. So then we get 68. Same goes to the sigma 1. Sigma 1, 253 minus with 68, then we obtain 171. Okay. So based on sigma 3 and sigma 1, then we plot the graph, okay, of the sigma effective. Okay. So then from there, the more circle and feather envelope are drawn in Q 4.5, from which C is equal to 0 and P is equal to 25 half degree. Okay. So the principal stress different at failure depends on the value of all round pressure under consideration took place. Okay. Here's by proportions, the expected value of sigma 1 minus sigma 3 is equal to 170. Okay. So let's say if we consider the 250 value, okay, so then the failure value of tau, okay, is around 100. No. Sigma 1 150, that's okay. Oh, so this is 200, 300, 250. So approximately the value for the is 170. The principal stress difference at failure depends only on the value of all round pressure which consolidation takes place approximately 250. Okay. So here's by proportion, the expected value is 170. Okay. Okay. So what would be the okay? Okay, determine, okay, if a specimen of the same soil were consolidated under or rounded of 50, okay, and the principle is different apply with the all 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 rounded pressure change to 350, what would be the expected value of principal stress at principal stress different at failure? Now 4560. Okay, so then we try to calculate tau is equal to sigma tangent 20.5. Let me use calculator. Okay. So tangent 20.5 times 250. Oh no, it is 119. 119. Oh, 250. Yeah. 250. Okay, anyway. 200. Let's see. Okay. 100 is 220. The simple difference. Okay. 1000. 25. Want to solve the last question before they obtain 170. Mau or 600. 250 plus 250. 600. 600. Okay, we already obtained the phi value and C value 0. Okay. The specimen of same soil were concentrated under an all-round pressure, and the principal stress difference applied with all-round change to 350. Okay, so that will be the then we need to plot the graph. So sigma 3 is 250, sigma 1 is 600. Sigma 3 if the sigma 3 is 250, and this is sigma 1 300. So this will be 600. There is no For example, this is 250 here. Then approximate the tau is 100. But I still could not get the last answer. Let me work it again and then try to share with you. All right, okay. So that is for the part 1. Okay. Later on, we come back with you on the last issue. So what will be the expected principal stress difference at clean? Okay. So there is some discussion on the more column circle. Okay. So we take a rest. Okay, then we will continue. Okay, at 12:45. Okay. For the last part for today. Okay. Okay. Before that, any question from what we have discussed?
No, sir.
Okay, because after this, there will be a lot of derivation. Okay, you need to look on the notes that I give to you. Okay, and also we will go for the slide as well. Okay, so we meet at 12:45. All right.